start again. So in the break there were a few questions. One was, what are these CIs? So these CIs are just constants. CI, these are constants in F2. So if you're a mathematician, then F2 is a nice thing. If you just want to know what it is, it's either 0 or 1. If you're an engineer, you might think more of those as a closed wire or as an open wire. So C0 just means there is no wire between that position in the state and the connection on the top. And if it's 1, then it is connected. Another one, I was saying that the sum of the periods is the is 2 to the k. So 2 to the k is the sum of the periods. And a group of people ask me, what if it's just ultimately periodic, not periodic? And then it's also plus the sum of the tails. This only kicks in if this is only ultimately periodic, so then you have if you have ultimately periodic, oof, then you have a picture where you have some tail and then you have a sequence where it rotates. So this part here, the length is the period, and this part is the tail. And this is the periodic part. So if your thing has not just periodic parts, which would be the circle, but has a tail, then you also get the sum of the tails for those things. We will always look at LFSRs for all detailed investigations. And for those, because we can go backwards, if you have SI equals SI plus R, you also can shift by 1 and have SI minus 1 being SI minus 1 plus R. So because we can reverse an LFSR, all LFSRs are periodic. So that's the difference between having a general function, which can have a multiplication in there, and something where it's just addition. If you have added a constant, you know what constant, you have added contents of one shift register, you can recover it back by just reversing it. If you have multiplied some numbers together, and you have the result of this in your final bit, but you're missing some of the other entries, for instance, if you squared S0, then you don't know where it came from. Well, okay, for the binary field, that actually doesn't make so much sense. Let's assume if you're over the wheels and you would square the first entry, you don't know whether it was +2 or -2 if you're seeing a 4 there. So for general functions and for general fields, you can't go backwards. However, if you have a binary field and LFSR, you can go backwards. So if you have a period going forwards, you will not go, you can't escape onto the tail. You will always go back into the periodic part. So that means the tail length is 0. All right. I did one example for that LFSR. I want to do another example for the S3 equals S0 plus S2. And then, of course, I have the sequence which is just 0 with repetition, so that one has period 1. So the start at the all zero state. And then let's start at some other state. So starting state, let's do the same as over there, where I was doing 1, 0, 1. So that was giving, as first we're outputting 1, 0, 1. Now it could be that I'm only in the repetition here, because over there, if I start with 1, 0, 1, it just repeated it 0, 1, 0, 1, 0, 1, so that's length 2. Now in this case, I'm optimistic, I'm writing all 3 of those, and then I'm supposed to take those 2 of the 3 and add them. Aha. This does give 0. So am I falling back into this pattern? So I'm now getting those 2, but I'm getting 0. I'm not falling back into this pattern. Aha. There's something different in this. So I'm adding all 3 positions. I had the 1, 0, 1 adding to 0, and then this one adding to 1, adding to 0, adding to 1. So it had just been these 2. In this case, where I'm just putting a tap on the outer 2, I'm getting a 0 as well, here. Now I'm putting a tap on those 2, I'm getting a 0. So I've now escaped from the next 2 sequence. I'm now adding those 2, I'm getting a 1. I'm adding those 2, I'm getting a 1. Adding those 2, I'm getting a 1. I'm adding those, so I'm still having a state that I haven't seen before. I have a 1, 1, 1 state, I'm getting a 0. I now have a 1, 1, 0 state, which gives me a 1. And now I'm back to where I was before. So this is the same state as this one. So how long is my sequence now? So I have these 3, and then I have 4 more until it repeats. So the sequence is 1, 0, 1, 0, 0, 1, 1. And then this thing periodic of period 7. Now we have that 7 plus 1 is 8, which is 2 to the 3, so we're done. Now, of course, we can analyze an LFSR by doing this. And if your computer is doing it for you, you can easily count. But it also takes a long time. It's kind of inconvenient, and I've been promising that these things are easier to analyze. So there must be a bit more. Now, today is going to be more mathematical. I hope you saw this, and if you don't know some of the pieces, one can read those out. So we will now use matrices, which you must have seen like in your first year as something in the algebra. So we use a matrix representation for the update function. So we have a state, and now I'm writing those as capital letters. So I have a capital letter S0, which is the initial state, so that's S0, S1, S2, till Sk minus 1. And then state 1 is S1, S2, S3, Sk minus 1, and then I get the function of S0 till Sk minus 1. Etc. And now I would like to write this as a matrix multiplication. So we're writing the updated state as n plus 1 as the previous state times some matrix C. So let's do an example from those before. So what does C look like? What we would like to have is that if we take our state, we may have, say, S0, S1, S2, and we multiply by this matrix, we're getting another length 3 vector, which contains S1, S2, and S3. So this must be a 3 by 3 matrix. In general, this one is C is a K by K matrix. Now, what happens if we put in this vector? We have a horizontal vector times the first column, and what it does, it takes S0 times the first entry, S1 times the second entry, S2 times the third entry, and outputs this one. So all we want to do is we take the middle entry here. So we take 0 times the first entry, 1 times the second entry, 0 times the third entry. Similarly for this one, we're just taking the last entry. So we're taking 0 times the first entry, 0 times the second entry, 1 times the third entry. Now, S3 is computed as C0 times the first entry, C1 times the second entry, C3 times the third entry. So S0 times C0, S1 times C1, S2 times C2. So these are the coefficients from the LFSR. So for example, if you had the example I just did, that S3 is S0 plus S2, then our matrix C looks like 1, 0, 1, 0, 0, 1, and then S0 is taken 1 times, S1 is taken 0 times, and S2 is taken 1 times. In general, if you do this, you will always have the left part of the matrix be like the unit matrix, but shifted down by 1. So the ones are not on the diagonal, they are one position under the diagonal. So you have the K minus 1 by K minus 1 identity matrix with zeros on top. That just means your shift being left. So in general, you have your matrix C, which is 0, 0, and then 1, 0, 0, 0, 1, 0, 0. And so those go down on this shift diagonal. There's all zeros here, all zeros there, zeros. So this one here is the K minus 1 times K minus 1 identity matrix. And then the last, so this just means you're shifting left. So this corresponds to shifting by 1 position. And then the last row, last column is C0, C1 till CK minus 1. So these are the coefficients. So if you continue with this thing here, so I have written my S1 is S0 times C. If I have an Sn, well, I have this Sn plus 1 is Sn times C. Now I can shave off another C, so that's Sn minus 1 times C squared is Sn minus 2 times C cubed. So each time I'm increasing the power of C and I'm reducing here, so the sum of those is always n plus 1. This was here. So in the end, that is the same as if I started with S0 times C to the n. N plus 1. I just said it's always 1 more. Now C is just some matrix. If you take powers of this matrix, it's k by k. They're only the first part. Well, okay, if you square these things, you only have 2 to the k entries in this direction. So eventually, this must repeat. So C is the k times k matrix. So eventually, we have that C to the I is C to the J, and let's assume that I is larger than J. So C to the I minus J is the identity matrix. For I multiple J. And if you hit this thing, let's call I minus J, let's call this thing L. But if you're looking at Si plus L, then that's the same as, let's just fast forward by L, and we have Si times C to the L, which is the same as I as times the identity matrix, which is the same as Si. This means that if C, the matrix C, has order let's call this order R, then now let's keep it by L, sorry, same as up there. The LFSR repeats after L steps. I'm calling L and not R because this might not be the period. If, for instance, you've been taking a matrix which has order 7, so it repeats after 7 times, you still might be putting in the all 0 vector. And the all 0 vector has a period length 1, even though this could have had 7. So this thing means by the lemma before, so by the lemma above, the period, any starting state, divides L. by knowing what the order of the matrix is, you're getting some upper bound on how large the thing can be. Now in the case of this nice LFSR, so for S3 equals S0 plus S2, I don't want to do computation because it will require me computing C to the 7 to finally get the identity matrix. But you will get this. So we get C to the 7 is IS3, and 7 is minimal. Also, it's prime, so there aren't that many choices of what it would be. So if C is not the identity matrix by itself, then if you get that C to the 7 is the identity matrix, then 7 is minimal because it would have to be a divisor. So it means in this case, the possible period lengths are 7 and 1. And those are exactly the ones we've seen. Now for the other example, the one where we're putting tabs on every entry, so that the S3 is equal to S0 plus S1 plus S2. For that one, we've seen period length 4, 2, and 1. Now, that tells us that the C must be an element of order multiple of all of those, but we don't know whether this means 8 or 4. Because, by the way, just a side comment, order is the smallest positive integer R, integer rule T with C to the T is identity. But this is something something about finite groups, in general, symbolic groups. So this is something I expect you to have seen in the algebra course. If you have not taken the algebra course and it's still here, this is something you will need. So look up what order means. So the second example, if you're taking the other one, so S3 equals S0 plus S1 plus S2, so that's the one which you've been running through there, then we have that C is equal to 0, 1, 0, 0, 0, 1, and then 1, 1, 1 is the last column. And now we need to figure out what is the order of that thing. So I'm writing C here, 0, 1, 0, 0, 0, 1, 1, 1, 1, times C, so that's 0, 1, 0, 0, 0, 1, 1, 1, 1. Okay, now that gives me, this goes the first row times the first column, so we're getting 0, we're getting next entry, we're getting the 1, so 0, 1, and I'm getting the 1. Next row is 0, 1, 0. And we're getting finally 1, 1, 0. Okay, not done yet. This is not the identity matrix. So I copy the thing here, F0, 1, 1. So this one here is C squared. Now computing C cubed. 0, 1, 0, 1, 1, 0 times 0, 0, 1, 1, 0, 1, 0, 1, 1. I compute this product here, so I have 1, 1, 0 as the first row. Next row is 1, 0, 1. And finally, last row is 1, 0, 0. And again, that's not the identity matrix. Now we know that we have to go till at least 4 because we've seen that one of the sequences has length 4. Let's just hope we're done now. As I said, it could go up to 8, but hopefully not. Unless I make a mistake, this will give the identity matrix, so I'm copying the C cubed here. That's 1, 1, 0, 1, 0, 1, 1, 0, 0 times 0, 0, 1, 1, 0, 1, 0, 1, 1. Okay, so obviously here, getting a 1, we're getting a 0, we're getting a 0. First row is good. Next row is 0, 1, 0. And finally, this is 0, 0, 1. So we're getting that this thing here is in fact the identity matrix. So we have that this C has order 4. And so all the possible orders we can see are divisors of 4. So this means C to the 4 is the identity matrix of 3 elements. So all sequences have orders dividing 4. And what we've seen is 4, 2, 1, and 1. Well, this sums up to 8, so we're also done. Okay, now I can wipe that part of the example. So at this point, we have translated something which is asking you to just brute force, just run this thing, which is fairly easy but doesn't give you any math, to the question of finding the order of some matrix. Now, if your best order finding is to just brute force it by doing the calculation of just done there, you actually make your problem just harder. Instead of doing something where each update is just a sum of things, we now, like we had to sum 3 things, and now we had to compute 9 elements times 9 elements. That's not a good deal. So this matrix is just a step on finding out more about sequences. So it's a necessary thing to understand, but it's not how we want to determine the order of our sequences, or the period of our sequences. But it does limit what periods we can find. So I would like to write this lemma, but I'm not going to give a proof because we've basically shown this. Lemma, if C has order L, then the sequences generated by it have periods of length dividing this L. But we actually would like to know more. We would like to figure out, like, how do I have to choose our CIs in order to get something of maximum sequence. So the maximum possible order maximum possible period for an LFSR of length. So we have length k. Then we know there's at most 2 to the k states, but we can't use the all zero state, because if you have the all zero state, it will just continue to be all zero. So this one is 2 to the k and then minus 1. And this last piece here is we're removing the all zero. Now can we actually always get this? I mean, in this first example, we did 2 cases and that's pretty much it. We want to have that the first coefficient is always 1. Okay, then we have this one 3. We could have delayed by 1 more, so we have a little bit more choices. But if the last one doesn't come in, we're basically grabbing 1 coefficient too many. So those 2 always will be 1. And then we only have 2 possibilities. One of them had a nice sequence of length 7, and the other one had this mess of 4, 2, and 1. So how to choose the CI to get this is 2 to the k minus 1. Is that always possible? And you want something that is faster than basically brute forcing. The powers of C. Okay, now you could say we already are faster than brute forcing the power C by forwarding the LFSR, but it's still the same number of steps. Each step is a bit more expensive, but nothing else. Now, when you took a class in linear algebra, you must have learned something about eigenvalues, and that eigenvalues describe a lot about the matrix. So, when you learn about eigenvalues, then you must have learned about the characteristic polynomial. So these guys are captured by the characteristic polynomial of the matrix. For now, I will only do the binary case. Yes?
Actually, many of the students here, I think, have never had a linear algebra course.
Okay.
So we don't
Who
know.
has seen matrices? Okay, matrices was still, for the majority, not too scary, and for the other ones, I hope you can catch up. I mean, this is the typical thing that you see in algebra as examples, so I expect that you have seen it. We won't need eigenvalues. We will use a characteristic polynomial, but I will define it now. So if you haven't seen this word, take the following as a definition, but this is only the binary case. So binary means I will not take any, I won't care about plus and minus. So for a matrix C, the characteristic polynomial is the determinant, it's one of these other scalar words, of C, and I'll for now briefly write minus, but we'll ignore this in a moment, C minus X times the identity matrix. Now, we'll do this in our case, this example. So we are supposed to compute the determinant of something which has x on the diagonal. And okay, as long as we have zeros on the diagonal, don't worry. So then we have nothing happens to these entries. Then you have another x on the diagonal. We have 0 minus x is x, and then 1. And all the way up till here, we're just entering x on the diagonal and have the 1 under the diagonal. So this rectangular matrix with the all 0 row on the top, and then the shifted ID matrix here is just now an identity matrix which ends with 1 and x here. Has a 0 here, 0 there, all zeros here. Then has C0, C1, Ck minus 2. And now here we have the Ck minus 1 plus x. So that's what it means to take C minus x times identity matrix. And okay, I said I'll ignore one, so I'll put plus there now. And then you're supposed to compute this thing. Now that's rather a monster, so we're going to do some small examples and then the general case. This thing has, well, it has k times an entry x. So this is a polynomial of degree k. So here we'll put a question mark, leave some space there, we'll have the formula here which starts with a big sum. And I'll do some examples. If you have a very short LFSR, which is just S0, feeds back into S0. That means we have the length 1, so we have a 1 by 1 matrix, and so we have C is 1, and so we have that I should give it a name, let's call this P. So P of x is the determinant of x plus 1, which is x plus 1. Let's do a slightly more interesting example. Let's take our case from before. So we have our S0, S1, S2, and all three are connected. And the output. So for that one, we said that C is 0, 1, 0, 0, 0, 1, and finally 1, 1, 1. So then we have that P of C is the determinant. I'm putting in x's on the diagonal of x0, 1, 1, x, 1, 0, 1, and then 1 plus x. Now, if you see a 3 by 3 determinant, there's a rule to compute this thing, which is you take the sum of the entries on the diagonals from up to down. So we're taking this and these, and then those come in with a plus, and the anti-diagonals, so the up right to down left, this come in with a minus. So that means we have that this is x plus x times 1 plus x plus, oops, this should be orange. That was bad coloring. This is the main diagonals, so they come in orange as x times x times x plus 1. This was the main diagonal. Then we have 0 times 1 times 0 plus 1 times 1 times 1. Now, normally this would be a minus, but we're in F2, so plus equals minus. And now we do all the antidiagonals, so we have 1 times x times 0 plus, now this one, 0 times 1 times 1 plus x. And finally, 1 times 1 times 1. Okay, there's a lot of zeros on the board, so I can just cross out these guys. Then we have a 1 times 1 times 1, the same as 1 times 1 times 1 here. So those two guys cancel. Oh, yeah, there's also the 0. So in the end, I have this product here, which is x cubed plus, there's something missing.
Shouldn't the last 1 times 1 times 1 be 1 times 1 times x?
Yes. And there's also some other x missing. So these do not cancel. Good. I'm glad that my pieces are not disappearing. Okay. So then from the first entry we have x cubed plus x squared. From this guy here we have plus x. And from this guy here we have plus 1. If we do the same for the other example of length 3, where we have S0, S1, S2, and only the outer ones connect, then we're getting that P of x is x cubed plus x squared plus 1. And in general, well, we can actually prove this up there. But for now, let me just write the result is, this is going to be x to the k plus the sum over ci x to the I, where I runs from 0 to k minus 1. And I said before we would like to have that xk, well, we're just setting xk equals 1 in order to reverse it. So this is equal to taking the sum from 0 I equals 0 to k over the ci xi using ck is 1. So very important, this is 1 more than the state length. And I have 1 minute for the proof sketch. So the proof works by induction, so we will take the first row. If you have never seen determinants, this will not mean anything. If you have seen determinants, this hopefully makes sense. So we develop for the first row. That means we're taking this entry times this determinant, all others are 0, and we're taking this entry times this determinant. So we have a proof sketch. So the proof works by induction. If you have that the first one, k is 1, then we see above. And else, if you have p of x you can write this as C0 times this matrix which is up there, which has 1, x, zeros. In this case, we're cutting off the rightmost column. So here we have the x's one above the diagonal, zeros here, and all zeros here, plus x times a determinant which looks essentially the same as what we had before. If we develop for the first column, then we have the x's on the diagonal, the ones below the diagonal, all zeros here, all x's here, zeros there. And now we chopped off the C0, so we started by C1, C2, till ck minus 1 plus x. And so this here is C0 times this determinant, which comes out as 1. This is a nice, easy one because it has just the 1 on the diagonal and 0 below, so it's easy to compute the determinant, just the product of the diagonal elements. And this one here is where we use the induction assumption. So this is C0 plus something similar. So this one is of dimension k minus 1, something similar. And if you make the induction assumption that up until k minus 1, the formula that we wrote up there holds, then, okay, we have now reduced it to something of dimension k minus 1, and we have an extra x, so we get out. I want to get to here because on Thursday in the exercise session we're going to see a lot of those examples, so you will need something where you can use matrices. So bring some computer which has computer algebra systems, say Mathematica or Sage or Paris, and you will compute some powers and some questions for them. Okay, that's it for today.